Today's lesson is going to be on intermolecular forces. If we take a look at our learning goal, it says that by the end of this and by the end of your work tomorrow in class, you should be able to explain how the physical properties of substances depend on intermolecular forces. So some questions. Why do some solids dissolve in water but others do not? Why are some substances gases at room temperature but others are liquid or solid? What gives metals the ability to conduct electricity? What makes nonmetals brittle? All these answers have to do with intermolecular forces. So here's a little overview of intermolecular forces. There are two types of attractions between molecules, in molecules, intramolecular bonds or intramolecular forces. Those are here in blue. Here, I just circled a couple for you. Intermolecular forces are these red squiggly lines in between molecules, and that's what we're going to look at. We've already looked at intramolecular bonds, ionic, polar, and nonpolar bonds. So now we're going to focus on the intermolecular forces. They have to do with the attraction. Again, the key word here is between the molecules versus the attraction between atoms within a molecule. All right, I'm going to erase these and sort of redo them just to make it a little bit neater. So we've seen that molecules can have a separation of charge. Okay, we basically have seen these partially positive and partially negative charges within molecules. This can happen in both ionic and polar covalent bonds. And remember, the greater the electronegativity differences, the greater the dipoles. What ends up happening is molecules end up being attracted to each other in a compound by these positive and negative forces, kind of like a magnet. So if we look down here, here, I'll write in a different color so you can see a little bit better. Maybe green. So there's a partially negative and a partially positive charge within one big molecule. Okay, that partially negative side is going to be attracted to a partially positive part of another molecule. So that attraction there, that's your intermolecular force, or we like to abbreviate that IMF. The second type of intermolecular force is a hydrogen bond. Now, hydrogen bond is a special type of dipole-dipole force that is extra strong, okay? Here's the reason why it's extra strong. It occurs when nitrogen, oxygen, or fluorine are bonded to hydrogen, making that bond very, very polar. Okay. If we look at the electronegativity difference for hydrochloric acid and water, look at the difference. In hydrochloric acid, when you subtract the two electronegativities, you get an electronegativity value of 0.8. In water, when you subtract the electronegativity values, you get a value of 1.4. That's almost ionic. Almost ionic, really freaking strong, okay? So because it's so strong, because the electronegativity difference is so strong when hydrogen is bonded to oxygen, nitrogen, or fluorine, we basically end up with an intermolecular bond that's about 5 times stronger than a normal dipole-dipole force. Because it's that strong, we give it a special name called a hydrogen bond. So now remember, these are intermolecular forces. So if I have a bunch of water molecules, okay, you have polar bonds within the water molecules, okay? This bond here, not a hydrogen bond. That's a polar covalent bond within a molecule, okay? So that bond right there is not a hydrogen bond, but it can form hydrogen bonds with other molecules. So I'll show you how that works. So that bond there is not a hydrogen bond, but if there's another water molecule floating nearby, it can attract here where I just drew in red. That attraction, that is a hydrogen bond. So make sure you keep that straight because that's a common misconception that students have. All right, here's another example, hydrogen fluoride. Okay, fluorine is so much more electronegative that the electrons get pulled towards fluorine, creating those dipole moments within the molecules and allowing the molecules themselves to connect together. Okay, so here is sort of a picture of those blue arrows again. Those are your hydrogen bonds. Those are your attractions between different parts of the molecule. London dispersion forces, okay? These are a special type of dipole where the atoms can attract each other but only for a split second, and it's basically due to the constant motion of electrons. So here's what ends up happening is that you have electrons. Here's one electron here, here's an electron here, and you have to remember that they can kind of move all over the place within their orbitals, right? So if they're moving all around, then for a split second, they might be over here. In which case, that makes this side of the molecule partially negative and that side of the molecule partially positive, but only for a split second. Okay? It happens sort of instantaneously. Oops, a second. It happens instantaneously, and the second it happens, it pretty much unhappens. What it does in that split second, though, it allows other molecules to push their electrons sort of over to this side, maybe over here for a split second, making other molecules partially positive and partially negative. So you do have a little bit of attraction between molecules here. The issue is this only happens for a split second, so it's very, very weak. Now, if I kind of take out all my pretty drawings for a sec there, this is what ends up happening. The electron cloud that is closer is closer, so it has more influence, and you do get a little bit of a push and a pull, but again, remember this only happens for a split second. That's what a London dispersion force is. Okay, so they're explained initially by a scientist called Fritz London. They are the weakest intermolecular force. These are the only kind of attraction present between nonpolar molecules. Okay, again, because if you have a nonpolar molecule, there's no way you're going to have a partially negative and a partially positive charge to create a dipole-dipole force or a hydrogen bond. But they still are found between all molecules. It also helps to explain how some nonpolar molecules can stay together to form a solid or a liquid. So most nonpolar substances are gases at room temperature, but some of them can be liquids and solids. How? Well, because there are some forces that hold them together, even though they're very weak. Here are some factors that affect LDFs and maybe create forces that are a little bit stronger, even though the individual forces are weak. The size of the electron cloud. So the larger the atom, the greater the London forces, because larger clouds are more easily deformed. Therefore, dipoles are more easily formed, and you get a sort of stronger LDF. If you look at the chart here I've got all of my noble gases in order from smallest to largest. And you can see that as the electron clouds get larger, the larger clouds are more easily deformed, and we can make these instantaneous dipoles more easily, and that basically increases the boiling point. What else? The number of atoms in a molecule. So the longer a molecule is, the more places along its length where it can be attracted to other molecules. So for example, a molecule like CH4 looks like this. Okay, only really has 4 spots where electrons are sitting that can kind of create an instantaneous dipole, okay? But if we look at C4H10, and I draw in all my H's, there we go. I've got lots more areas, lots more electron clouds that can be deformed, lots more potential to have those instantaneous dipoles. So what ends up happening, the dipoles end up being a little bit stronger, and again, my boiling point increases. Oh shoot, I should have erased these answers. Which has the higher temperature in this case? MgCl2, magnesium chloride, or phosphorus trichloride? Remember, this is a metal and a non-metal, so this is an ionic compound. These are 2 nonmetals. This is covalent. So automatically, what's going to have the higher attractive forces the ionic compound. Higher attractive forces equals higher boiling point. Okay, so here's another example. Which of these two molecules has the higher boiling temperature? Best way to figure this out, draw them out. So CH3NH2 looks like this. And again, you guys should know how to do this because you all know how to draw your Lewis dot structures. And CH3F looks like this. Okay. So notice in both cases, you have nitrogen here that's got sort of definitely a partially negative and a partially positive charge. And you've got fluorine here that's more electronegative than carbon. So you definitely have polar bonds in both. They're both polar molecules. They're not symmetrical. So now which one has a higher boiling temperature? Well, hopefully you can see that here we have a nitrogen bonded to a hydrogen. Bonded to a hydrogen. That means that it can make hydrogen bonds with other molecules, giving it much stronger intermolecular forces, making this one the one with the higher boiling temperature. Other physical properties of liquids, we have surface tension. So this is responsible for the formation of bubbles and liquid drops, soap, the meniscus, and as well the rise of liquids in a capillary tube, so which is called capillarity, the absorption of liquids by porous substances, and the ability of liquids to wet a surface. This is really important for water insects because it allows insects to walk on water, which basically means that the weight of the insect is not enough to overcome the intermolecular forces between water molecules. You also need to know, here's some probably two new definitions for you, cohesion and adhesion. Cohesion is the water molecules are attracted to each other through cohesion, which is the attraction between similar particles because of polarity. Adhesion is the attraction between unlike molecules. So if we look at my little picture here, when water is placed in a glass container, the forces of cohesion overcome the forces of adhesion, and water can climb up the glass. So that means in here, where we have water, the water molecules want to bond to themselves more than to the water molecules can bond to the sides of the glass container here, so they can actually climb up the container, creating that meniscus effect. Whereas in mercury atoms over here, Hg, the cohesion between the molecules of Hg is stronger than the attraction to the glass. Okay, so therefore here the molecules are going to want to bond together and get away from the glass, creating that sort of reverse meniscus look. All right, last one is capillarity, and this is the movement of liquid up a narrow tube. Again, same thing as over on the last slide. It has to do with cohesion and adhesion and which forces can overcome each other. So since water is attracted through adhesion to silicon dioxide, which is glass, it will force water up the tube, but this can't occur in mercury because there is no adhesion to the glass. And that's it for today. We'll see you in class.